get started. 吕阳可以开始。
Okay. Hi everyone. Today I'm gonna lead this paper reading, which was worked out by both me and Lei. And the title is Thermal Barometer of Carbon Dioxide-Rich Silica Under Saturated Melt Constraints Cratonic Lithosphere Thinning Through Time in Areas of Kimberlitic Magmatism. So the first author is Chen Guangsun, and he's graduated from China University of Geoscience, Beijing, and he went to Brown University for his PhD, and he went to 3 places for his postdoc, and now he's in University of Texas as the assistant professor. And his work includes this following topic, which is carbonatite peridotite reaction and kimberlite and deep carbon cycle and geothermal barometer and cratonic evolution. So in this paper, they investigate the craton destruction problems. Usually our conventional views of cratons are buoyant and stable, but there are some obvious craton destruction events such as Archean, Wyoming, and North China cratons. These destruction events raise 2 questions on the cratonic lithosphere's stability. Question 1 is, does lithosphere destruction occurs as singular events locally or as repeatable process for cratons globally? Question 2 is, what may be the mechanism of lithosphere thinning for cratons on a local or global scale? So with these 2 questions, they need an estimate of cratonic lithosphere thickness through time by global database. In previous study, people used peridotite analysis to get lithosphere thickness, but the analysis thermal barometers has a major source of uncertainties from the thermochemical perturbations, because mineral-based thermal barometers tends to record the temperature and the pressure wrong due to the diffusive resetting. And the second drawback of previous study is the mental analysis has a limited number, so it's hard to understand the temporal variation in the lithosphere thickness. Since the analyses are not good enough to investigate the problem, the authors, they think kimberlite are way more suitable, because the first kimberlite magma is from the lithosphere root. It can carry unique insight into the unstable cratonic lithosphere. And second, there are amount of kimberlite samples data which can be easily used. And the kimberlite also have a wide range of ages, so they can achieve the through time and global investigation goals. The other important thing is kimberlite's final equilibrium with peridotites occurred at LAB, which is lithosphere asthenosphere boundary. So they use this information to limit the lithosphere's depth by kimberlite. However, there are no reliable thermal barometer of strongly silica under saturated mantle-derived melts. You can easily see from this figure, they test the exciting thermal barometer from previous work. You can see from here the y-axis is the predictions minus experiments results based on the previous parameters. So if the silicon dioxide less than 40%, the results are not good. The prediction based on the previous thermal barometer produce a huge error. So you can see the pressure has 13% upper 13 GPa error, and at the same time the temperature has 450 degrees Celsius error. So, but when the silicon dioxide more than 40%, their barometer seems good, but less than 40%, they are not good. So, so they want to build a new barometer based on the silica undersaturated melt, where the kimberlite come from. Then use this new thermal barometer on a global kimberlite dioxide to get the results. And then they collect 202 high temperature and high pressure experiment data from literatures. This data especially includes low silica dioxide content with some volatiles. During this thermobarometer building process, they find this aluminum oxide contents of experimental melts derived from the garnet peridotites has a relationship with the pressure. When the pressure increases, the aluminum oxide contents decrease. So it is a pressure dependent process. So they, based on this, they build this new barometer, because the composition of the mantle garnet is sensitive to the pressure, the power of activity in garnet can be approximately as a function of pressure. So based on this principle, they build this temperature dependent barometer, and also they build this thermometer. This figure shows that their new barometer reproduced the experimental data well, which has significantly improved over the previous model. So, and the author also constructed a global data set of natural kimberlite compositions by download from the GeoRock database. It includes information of locations, eruption ages, and major elements composition of volcanic kimberlites. They also add some eruption ages and cratonic setting that were missing in the GeoRock database by checking the literatures. There are around 1,000 data, and they do data processing before apply their new barometer. First they exclude the low magnesium oxide contents, and the second they exclude the samples contaminated by crustal materials or mantle denolis. Third, they estimate the primary melt compositions of natural kimberlites by adjusting olivine fractionation or olivine accumulation until the magma achieves chemical equilibrium with mantle compositions. So after these three steps, data felt.
So why magnesium oxide less than 88%?
You mean the first data processing?
Yes.
I forgot, but yeah, I forgot, but I can check the paper later. Okay. So after that they applied this thermobarometer on this data set, and the results shows that the most of data falls within the 1130 degrees C to 1730 degrees C, and 2.5 to 9.5 GPa. And the light green range here is defined by the cratonic mantle thermals, and the blue band in here shows that the carbonation freezing fronts, which I'll explain later. And the most of the data they marked as cluster on craton or off craton are the data they used later. And the global samples they marked here is the data they excluded, but they still predict here. This right in this figure C, they shows that in this case study, these data are modified by the lithosphere, so they excluded. This is a case they excluded the samples, and among the global kimberlite, less than 4% samples fall within the pressure temperature range defined by the cratonic mantle thermalist, which is the light green range. So this 4% of samples likely at a final equilibrium within the lithosphere or directly derived from melting of the lithosphere. And about 16% samples also show the temperature lower than the present day ambient mantle, but greater than the cratonic thermals at similar depths, indicating that incomplete re-equilibrium with the lithosphere during transport, which means they also contaminated by the lithosphere. So yeah, so they excluded them at later results.
Wait, Ben, I didn't really understand. So here for global samples, what do they mean, global samples? So how did they choose the temperature pressure for global samples?
Actually, they didn't say clearly that in this figure how they divide the global samples and the cluster on craton and the cluster off craton. Even they say a lot of things about the blue and the yellow mark, but for the global samples, what I understand is they at the data processing pre-processing, they failed some data because there are some samples are altered or contaminated by the lithosphere or the later process.
Okay. So for the global samples, that they still use their thermometer and barometer to calculate temperature and pressure, but they think that some of those global samples that they have already been altered. Okay.
Yes. Yeah.
I see. If that is what they think, and then what does this clusters mean? So that's
okay.
I didn't really get it.
Okay. Yeah. Sorry, I forgot to explain. Let me get back to this data slide. You can see from here this data from when they collect this data, this data come from like a 1-by-1 literature, and in one literature the kimberlite, there are maybe many samples you can see here. There are maybe 20 or 10 or something samples, and they are from a field they call it. Because there are many kimberlite samples, so they clustered this kimberlite in one cluster, or means one field. It's maybe one place has one name. So that represent this
okay.
Like
so
rare...
in one place. So in one place, basically they're trying to get average. Is that what what I understand, right? But place, for example, in the very first one, the Amazonia, Guanayamo, then they may have, I said, 2 samples, I think. Then that's the temperature pressure range that they get, I suppose. And then in the second place, they have 27 samples. They mean 11. That means 11 ones are uncontaminated.
Yes.
And then you get the temperature and pressure range of those 11 samples.
Yes, right.
If my understanding is right. Okay.
Yeah. Yes. So, and there are some samples they didn't choose because they didn't pass the filter, data filtering. Yes, and yes, and so they, sorry, let me. So they use this sample didn't contaminated by the lithosphere to define this green area, and they find that sorry, the x-axis is the age and the y-axis is the lithosphere thickness. So first they use all this data to define this green area that shows the lithosphere are thinning through time. And if you can see this this different marker shows here that they just see that if you see this pink triangle, and these are also the pink one. So they're seeing that the pink one are the pink one's lithosphere thickness are decreased through time. But in the right figure, they are add some others kimberlite clusters or and the off craton samples. You can see such as this green, the green one, that the later sample are not less than the frontal one's lithosphere thickness. So they think some sample are stable, or which the sample represent the craton are stable, and or even they are thinking someone are thinking, and they also put the off craton data in this figure. This estimated lithosphere thickness of off cratonic regions agree with the global trend, which is defined by this data in figure 8, sorry, suggesting that the observed lithosphere thinning at cratons likely has also been operating at non-cratonic continental routes. So they think the off craton continental routes has the same unstable condition with the cratonic routes. And they use this thermometer on this data set. They get this result that some samples temperature are the same with the ambient mantle, and some kimberlite sample are not, and they think the high temperature kimberlite are from the house bath, and the other one are derived from the mantle. So, and there indeed are two theory of the kimberlite generated process. So and they have proved that these two theories are both correct, and they also check these samples locations. They actually are same overlaps with hotspots locations. So they confirm that these two theories are actually both right. And in the last figure, in this figure, they showed that the axis is the age, and the y-axis of the first axis is the log TP ratio, and the second y-axis is the extent of thinning. So basically, the first one is the log TP ratio one. They are saying that because of the temperature pressure ratio increased, which represent is hot subduction, and hot subduction, which means is a shallow one. And when the log temperature is lower, then that means cool subduction, which is deep subduction. Then they're trying to say that when the basically based on their results, because they're showing that their kimberlite frequency is increased from 2,000 billion years to now, and which means they think there are a relationship between the deep subduction and the kimberlite frequency increasing. So basically, they are saying that there are more and more deep subduction, and this deep subduction will produce more and more kimberlite. So, and in the same time, the more and more kimberlite frequency, and which produce the more and more lithosphere cratonic unstable, which is thinning the cratonic lithosphere. Yeah. Now and then they get the three conclusions that the equilibrium depth of older kimberlite mantle melts are mostly deeper than those of young ones, and this result can be interpreted as evidence supporting the establishment at cratonic and off-cratonic mantle globally since about 2 billion years, with an extent by thinning by about 150 kilometers, and the asthenosphere of the carbon dioxide rich melt enhanced by deeply subducted carbonate oceanic crust is a key factor modulating the erosion of the thick lithosphere over the ambient mantle and mantle plume through times. And the kimberlite didn't erupt. The kimberlite which didn't erupt through the lithosphere, they have the lithosphere root reservoir, and this melts chemically mechanism and weaken the lithosphere roots, and consequently they disrupt by the convective mantle. So that is the lithosphere roots unstable results. And that's we also mentioned this CFF, which is carbonation freezing front. So this figure shows the entire process of the kimberlite, how the kimberlite eruption, and how kimberlite affect the lithosphere roots. And Chen Guangsun mentioned this figure in his 2019 paper. And basically, they are trying to say that migration of the proton kimberlite melts directly from the deep upper mantle to surface is hindered by the carbonation freezing front at the cold, thick lithosphere root. When transition fractures or fractures zones are activated by the tectonic process or mantle plume actives through this channel, primary kimberlite melts can rapidly migrate across the carbon freezing front, and some may successfully reach to the surface, but it depends on the geological structure. If they failed eruption, this kimberlite can chemically metasomatized more and weaken the lithosphere. And such a weakened lithosphere, method of lithosphere roots is then radically destroyed by convective removal. So, yeah.
Please keep on this page. Okay, so if in this figure, according to Sun Chengguang's perspective, then not this one, Sun Chengguang's figure.
Yeah.
Okay, so according to this one, if according to his 2020 EPSL paper, then if the temperature and pressure of those kimberlites equilibrium conditions, if we plot them in this figure, this cartoon figure, then where should those where should those places be? So I don't think they are at the, let us say, the slab boundary. That is not a slab boundary, temperature and pressure. That should be, so that should be the carbon, let's say, barrier or something like that, CFF barrier, temperature and pressure. Is that right?
Yes, I think they're trying to say is the LAB, lithosphere thermal boundary temperature.
And then that is also the, let's say, carbon, let's say, failure barrier, right?
Yes.
They want to say this carbon
freezing.
failure, blah, 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 freezing barrier is the same as a lithosphere, statinosphere boundary. And that is the temperature and pressure that they, let's say, calculated according to a thermometer, barometer. They perform experiments in this one that they do. Okay, go ahead. I just want to make clear what did they say. Okay, good. Go ahead.
Okay. So the last page is from Giuliani that 2020 PNAS paper that basically they are saying that some kimberlite source are from LLSVP and some are not. And I think this confirmed that what Sun Chengguang were saying that some of the kimberlite are from the hotspot. And what I know is that hotspot are fall within the LLSVP area. So I think their conclusion are confirmed each other's. So yeah, that's all.
No, I don't think that they really confirm each other. From my perspective, people want to link the LSVPs with the hotspots. So that's only in terms of temperature, but temperature itself is not enough for kimberlite eruption to occur, because I think Sun Chengguang trying to let's say, Guani and Sun Chengguang's work that they're trying to combine two things together. It looks like they are saying different things but correlated, is that Sun Xuanguang want to say, okay, the subducted carbon, that's the reason for generating kimberlite, but it also needs the hotspot. And Gulianis want to say that those hotspots that come from the LSVPs, but LSVPs without the carbon probably will not generate kimberlite. That's I think what's self-consistent with what Sun Xuanguang trying to say, unless there are some other carbon source that are really primordial. Okay, that's my interpretation. Okay, that's good. I mean, when we read the paper, on the one hand, we interpret, we see the presentation is good. We want to interpret what the author is trying to say, and then look at what the reasons, evidence at least for that. So we want to make clear what people are trying to say, and then and what the evidence are, and then but we should also be critical about which evidence are solid, which evidence are not, and are there any logic mistakes in their statement, and in the end, that whether that is convincing to different audience. Okay, let's move back to the beginning and let's go through it again. Maybe I can add a comment. Everyone feel free to leave some of your comment. Yeah, please go back to the first page.
Yeah.
Okay, so for the author, Sun Xuanguang himself, that his PhD work worked on the rare earth elements, which are the elements that has relatively low diffusion rate, and therefore he calculated. I think there's a thermometer, maybe barometer. I'm not sure. I think thermometer. So that using the concentration of rare earth elements, especially in the core part of these minerals, then you could calculate the temperature, because they developed that thermometer with the advantage that rare earth elements diffuse very slowly, and therefore what they record should be the temperature in the mantle rather than the re-equilibrium temperature, because for metals analytics, they can move to shallow part, or they could be influenced by the host magma, so like a kimberlite melt, and then the minerals re-equilibrate. So for some elements that are trying to diffuse fast, for example, water diffuse relatively fast, and from zoning, some other elements also diffuse, and therefore the corresponding thermometer or barometer might not be accurate. Even for aluminum, I think it's something open for discussion, but for rare earth elements, those are the ones that diffuse the slowest. So that's some of the reliable ones. So Sun Xuanguang worked on that as his PhD work. Later on, he worked on different kind of stuff. And when he moved to Rice University, working with Raj Dasgupta, and Raj Dasgupta has been working on carbon cycle for a long time. And then he and another PhD student, so they are trying to work on the evolution from carbonated magma to peridotite melting. So they are trying to look at the transition for that, because actually that's one of the regions that has been relatively under investigated before, because people have been understand a lot about hydrous and non-hydrous peridotite, or peridotite add a little bit of carbon on it. But if you look at the whole full range, how it evolves, people doesn't know this so well. So they work on that. And this is related to carbon cycle, yes, and another on kimberlite. And that's what they're trying to write this paper and another previous paper about. So actually, different people have different ways of reading paper. And for you, maybe you read the introduction, then you read the that's content, look at conclusion, but some people don't. For example, for me, I read abstract, then that's it. And then I look at acknowledgement. Some people directly look for acknowledgement, and some people directly go to references to see whether the author cite his or her paper or not. So there are different ways of reading paper, but bear in mind, introduction might be the last part people are going to write, because that might not be a real intention of the authors. I didn't mean this paper is not the original intention. I mean, in a lot of studies, introduction and might not be the intention, the original intention of the authors. They may want to work on something else, and then it turns out to be like this, and then they find an introduction for it. Okay, so now let's move to page 6. Okay, page 6. Okay. So for this one, anyone has any comment? So for this Puterka, as well as Terry Plank, force barometer, what barometer they use? Did they use a garnet aluminum content or something that make it really off? Obviously, some of the blue dots looks like has never been, let's say, are not the ones that not used, I suppose.
Well, I'm not sure they describe this detail on this paper, but basically he's just say he tried the previous work.
Yeah, but we should know what the previous work about. Yeah, he tried
yes.
it. Well, you could trust the speaker, but you should always evaluate things by yourself. I think this is also related to what we are trying to do for your project, Ben. You should know because you are working on different thermometer, barometers, you should know, or what people have been used, what the pros and cons for that. I don't know what's the pressure range that are reasonable for previous people's work. Yeah, you should know. Okay. Any other people's comments? Similar for thermometer. Some of this like the 400 degrees. I think this must be something really outside the range of what the people really propose. Any other comments from our participants? Okay, next page. Page 8.
Yeah.
Page 8. Okay, so that's what I do. So for them, they are measuring the, so for this, their thermometer to work out. So they're trying to use equilibrium what or melt with what. So they need composition of both olivine, garnet, pyroxene, and melt to figure out the pressure or temperature. So in Sun Chengguang's work, what are input parameters? So they're trying to build a model. You need to have some input parameters, then you have output parameter of temperature and pressure, right? So what are the input parameters? So do they need the composition of all these phases, or they only need some of them, or they only need the melt composition? That's enough.
What I understand is they input the kimolite compositions. I think
they just need the melt composition. They don't care what's the composition of olivine or garnet.
Yes, right. I think that the other olivine, garnet, pyroxene is represent the mantle conditions, mantle compositions, right? I think they're trying to reach equilibrium between the melt and the mantle, the ambient mantle.
Okay.
Yeah.
Okay. So
And-
okay. Okay, next one. Page 9.
Okay.
Hello, can you hear me?
Yes, yes, please, Lei, go ahead.
Actually, about this page, because we discussed before, and but I don't know much about the traditional empirical barometers. So even though I read this paper, and I still don't understand the barometer and thermometer calculation mechanism very well, such as this page, the new barometer. They also give us the new temperature dependent barometer to quantify the melting pressure. But my confuse is that how to define the temperature. Is it an assumption, or if so, how to assume this value? Assuming that the different value will have an impact on the calculation of the pressure, and I'm curious about this.
Okay. Okay. My understanding is that the rationale behind it is that some elements are sensitive, or to a certain extent, we could say, okay, the partitioning coefficient of an element in the solid phase, either in olivine, garnet, or pyroxene, and the melt, is highly sensitive to temperature or pressure. Then people use that to quantify the temperature and pressure, and sometimes not just one element. So it's not sometimes not a partitioning of one element. It could be the partitioning of 2 elements or even 3 elements. And then people call that exchange coefficient. So the reason, for example, aluminum could stay in the pyroxene. And then with increased pressure, for example, maybe the aluminum doesn't want to stay in pyroxene, they want to jump into the garnet. And of course, the partition coefficient becomes different as you increase the pressure. So not only for aluminum, but also magnesium, iron, for these major elements, they all behave slightly differently under different temperature pressure conditions for their partition behavior. So and we'll go to more details into the Gibbs free energy, as well as the different crystallography, the bonding energy between this element and different elements in different crystal structures. So the rationale, I think, behind that is that normally when people choose a barometer, people prefer to choose the system. For example, melt with olivine, for example, or melt with the CPX. Think about petroleum paper in 2020, CPX melt barometer. So for those systems, normally people would choose a system that if you want to quantify for barometer or pressure, you want to choose a system that is insensitive to temperature, or vice versa. If you're going to want to do a thermometer, then you want to do a system that is with its partition coefficient sensitive to temperature, but not so sensitive to pressure. That's preferred. However, it's not perfect. Sometimes, like say, both temperature pressure has effect, but maybe they fall into a certain line. For example, the partition coefficient or the distribution coefficient evolve with both temperature pressure, but maybe they fall in a line so that you could let both to evolve. So think about the phase boundaries. When we see phase change, some phase boundaries before temperature and pressure curve. So that's also okay because you choose a wide combination of temperature pressure as a curve. And if we can get multiple thermometer or barometer, then you could see the cross section, the crossing point of different curves, and then you could get a more accurate constraint temperature pressure. So I think the rationale for that is like that. but I don't know in detail in this one how convincing it is for the parameter. It looks like it's also temperature dependent. Actually, I don't know what the other. There are some other symbols here, like cilia, phi or something. I think those are the ones, maybe they are constants, but I don't know how strong sensitive the temperature are. Maybe one way to test this, that we get a wide range of temperature range, maybe 1000 degrees C, another put it 1400 degrees C. Let's see how much it this variation cause on pressure. So maybe that's one way to figure it out. Okay, I hope I explained some part of it. Yeah, and I think it makes sense for this work that they're trying to look at the melt composition, because in the end, what you see in the kimberlite magma is that, okay, it's a melt composition. You just don't see the exact minerals they equilibrate with it. Because for the metal xanoliths that this kimberlite melt sample, they are not, they might not be equilibrium with the melt, because they are just happen to carry by the kimberlite. They have not been equilibrated. Actually, I would be more interested to see the comparison between the xanoliths and the kimberlite melt. Ben, do they compare that? The kimberlite melt calculated temperature and pressure, and the xanolith temperature and pressure.
Well, no. Actually, before they get to the kimberlite part, they're trying to argue that the xanolith is now it's wrong. So they didn't mention the xanolith results later.
Okay. So
Yeah.
why they say it's wrong? I mean that could be different. I mean, xanoliths are there. You have kimberlite brought them. So to me, that there are parameter and thermometer for xanoliths. I mean, even Swinton's own work, rare earth elements, they calculate the temperature of the xanoliths. I think, to me, this is a bit odd, because to me that at least if you plot the xanolith temperature pressure and then you plot the kimberlite temperature pressure, then the temperature should be below the xanolith to make sense. Anyway, it's odd.
Yes, I think maybe you're right, but the data from the xanoliths, I think it's hard to get, because it's easy to get just kimberlite composition and some kimberlite information. But if you want to get the xanoliths, you have to like our work, you have to compare with the different mineral in one xanolith, so you have to matching or something. So
Okay.
maybe it's harder to do this work.
Okay.
So
maybe what do? You could to plot them in the future. Let's see.
yeah.
I just have intuition that this it can be a test. I don't know whether it's right or not. It can be a test for the barometer thermometer Swinton proposed here, because it will be funny and interesting if you plot your xanoliths that are all below the kimberlite. Of course, that doesn't make any sense. You cannot. That means something that's wrong. If that occurs, okay. Okay, could you turn to page 13?
Yeah, sure.
It's an important one. So for this probability density, what do they mean here?
Well, I think they mean that all the kimberlites they are trying all the kimberlite samples. So they put a maybe
I know there must be a certain probability. For example, if the most outside circle the probability is like 90%, and then you have the second circle maybe 80% or something like that. I think that to me that's something that makes sense.
Yes, but I forgot this detail. I must check the paper for this probability density. Let me check it. Oh. I think they didn't mention a lot about this circle they plot.
Oh, okay. Okay. But here they didn't see they did see a little bit difference between class on craton and off craton. So on craton is slightly deeper. Is that right? But to me, that looks very similar, except like say 2 or 3 clusters.
Yes. Yes. Because in this figure they didn't show the age and the depth information, and if you look at the other figure, you can see the you can see yes, maybe some of cratons, off cratons, they can't give some label like the Atlantic craton or something, so they can't compare with each other. I'm not sure. Yeah, this off craton have how much difference with the on craton samples.
Okay, and it's also interesting that for early ones, for old samples, they don't have off craton ones. Only the young kimberlites they have off craton samples at all. Not because that also based on the assumption of the 2019 EPSL paper. So yeah, for less comments, I think we could ask the speaker. You could ask the speaker like on Wednesday. Okay, let's get back to this. So for depth, I don't know. That they really have to depend on their 2019 EPSL paper to draw this line to say, okay, this kimberlite melt. Because even if the cartoon is true, those kimberlite, they are, okay, they have to be accumulated according to the model, accumulated at the lithosphere, ionosphere boundary. And that accumulated melt depth, that is the, how do I calculate? Okay, freezing front. Freezing front.
Yes, I think this is the top of the freezing area. This is a cap.
Cap. So that is the. So what they want to say, if the temperature is higher than that, it won't freeze. It'll become melt. So what do they mean freezing here? I think they want to say redox freezing, or is a carbonated melt and a carbonated mineral. To me, that's also freezing,
right? Yes, I think it's not redox freezing. It's carbonatized.
So it's just a carbonated melt.
Yes.
Melt temperature. Okay.
but I think that's much lower than that. The carbonated period at the melting temperature is much lower than that.
Okay. Oh,
I think that's very low. Carbonated period at the melting temperature, according to Dasgupta 2006, up to 10 GPa, that should be, let's say, 1300 degrees C or something like that. So here is almost 1600 degrees C. I think it's too high. Maybe I'm wrong. Maybe they put more carbon here, then let it elevate a little bit. But but to me, it's still a little bit odd. Is that okay? How could the temperature? So how could those kimberlite temperature that? Okay, so they also want to say that there's a hot spot. You have a
yes,
temperature.
right.
Otherwise, you could not have ambient metal temperature to generate kimberlite.
Yeah,
Okay.
right.
Okay. I probably have this been speaking a bit too much. Any other comments from other participants?
I have a question about this slide 6. I don't know if I move it to it now. Anyway, I'm not sure the kimberlite, if the kimberlite have a remain problem, like they are maybe some old kimberlite are just gone, and the new one are just kept because the tectonic process. So if that's true, and then if you change the waxes to any proxy, then you still can have this. You still can have this figure because you always get the new young kimberlite frequency higher than the old one, right?
Yeah, I think Ben, you are raising two questions. I think they're both possible. One is that old kimberlite is not well preserved, likely. For example, we didn't see old non-cratonic kimberlite probably ones have been destroyed or they have not been preserved. So if they are, we count more here, then they won't draw this. Maybe the frequency is much higher for the older ones. And yeah, and actually, I think this is also related to what Lei's work. I think Lei's data-driven work now, that is also related. If they want to subduct some carbon, okay, if they only assume it's related to subduction slab, then probably that's okay. Then the amount of carbon in the lithosphere doesn't matter. Not really. To me, that if this is true as what they draw here as a deep carbon flux at the cratonic roots, then more carbon flux will generate more carbon or more diamonds. So if it is true like this, then we're likely to see an increase of carbon abundance in the lithosphere. Maybe not. We'll see if the data could tell us whether it's right or not.
Yes.
Yeah, Lei will tell us probably at the end of this year whether it's true or not. Okay, I think they do provide data set that's useful for us. let's say they have kimberlite age, etc. Although it needs more work from our side, but I think they do something that is useful. I think, at least. So how many rows of data do they have? How many kimberlite analysis do they organize so far? Do they have 1,000 or something?
Yes, 1,000, more than 1,000, I think. Let me check it. 1,400 data they used.
Okay. Okay. That's something that's useful. Okay. Okay. Thank you, Ben and Lei, for putting this up. Let's hear the speaker on Wednesday. I think it's interesting work and also interesting topic. It's interesting because if you talk about origin of any type of the rocks, I don't think you could publish Nature or Science paper. But you talk about kimberlite, it's still possible because something that people still not fully understand. Maybe chromatite a little bit, but I think kimberlite is more trivial than that. And talk about the minerals, then pretty much only diamond could make the spotlight in terms of what people really interested in and still make some discoveries. Okay. Okay, that's good. Have a good evening, everyone. Bye-bye.
Bye.